Welcome to my online seminar on LEDs. In this video, I will explain the basics about lighting. This includes the spectral power distribution, color temperature, and color rendering. Feel free to subscribe to my channel, where I will post new videos on lighting and LEDs, for instance. This figure shows the electromagnetic spectrum. The part of the spectrum which is pulled out with color devices is called the visible spectrum. These are the wavelengths that human eye can observe. The visible spectrum frequency ranges from about 380 nanometers to approximately 760 nanometers. Wavelengths located at 380 nanometers are perceived by man as blue-violet light. The wavelengths of 760 nanometers are perceived as red light. The remaining wavelengths are not visible to humans, but if you find yourself in the range of about 800 nanometers IR region, humans will be able to feel the heat radiation. Other living organisms on Earth are able to see wavelengths that humans cannot see. There are, for example, bees which see UV wavelengths, and on the other side of the spectrum there are rattlesnakes which see IR wavelengths. This diagram shows the sunlight spectrum in the absorption lines and the thousands of combinations. At the top right it is the infrared wavelengths, and at the bottom left it is the ultraviolet wavelengths. In scientific work with color and radiometry, a spectral energy distribution is utilized to provide an overview of the light surge and its power distribution of wavelength. SPD, a short form of spectral power distribution, is almost always included in light measurements and may look completely different depending on the light surge being measured. A spectrum can generally be described as a continuous spectrum, a line spectrum, or a mixture spectrum. An incandescent light will emit light with a continuous spectrum. A luminance light, such as fluorescent tube and discharge tube, will emit light with a line spectrum. LEDs emit lights having a mixture spectrum. As previously mentioned, the solar wavelengths lie above a large part of the visual spectrum, but also above a large portion of the areas in the ultraviolet and the infrared region of the spectrum. Because of the breadth of wavelengths, the sun will always be the greatest color rendering light source. I will talk about the different spectral energy distribution in this seminar. A shows an incandescent bulb spectral energy distribution with CRI of 99. Incandescent bulbs have a warm light and reproduce colors well. Note that the energies are spanning the entire spectrum. B shows the spectral energy distribution of a white phosphor-based LED with CRI of 87. Note the peak in the blue area. This is blue LED which is coated with phosphor to create white light. Depending on the phosphor composition, LEDs may have values of CRI 98. C shows the spectral energy distribution of a fluorescent CRI 80. The fluorescent tubes has a more mixed spectrum compared to the incandescent bulb and the phosphor-based white LED. Many say that fluorescent light is far from optimal for the human eye because many colors in the spectrum are missing. D shows the spectral energy distribution of a street lamp with CRI of 90. Here the focus is on extra high energy efficiency. This is seen by the fact that almost all the energy is located in the yellow-green region, where the eye is the most sensitive. The light surge reflects yellow-green color well, but almost all other colors are not reproduced properly. The color temperature for a given light surge, expressed in Kelvin, are logarithmic. That is to say that the same change at a low color temperature has a greater visual impact than if the change occurred at a higher color temperature. Color temperature changes between 1000 Kelvin and 1200 Kelvin with those have a greater visual effect than color temperatures between 6000 Kelvin and 6200 Kelvin. As the picture shows, the color of the pot changes as the temperature is raised. The higher the temperature, the colder the light feels, and conversely, a lower temperature will cause a warmer light. In everyday language, we speak of cold and warm light. The color rendering properties of a white light surge are measured and specified by CIE Technical Report. Method of measuring and specifying color rendering properties of light surges. The measurement, or rather the calculation of CRI for color rendering index, is made on the basis of measurement of the spectral distribution of light from the white light surge. When calculating the CRI is used a reference light surge, which is as close to the black body as possible. The light surge illuminates, in quotes, 14 standard colors, and then the result will be compared to the test light surge. Used are 8 standard colors. To find the average, there may be supplemented by a further 6 colors to identify the light surge's further knowledge. In a specific color rendering index, it is necessary to supplement by a further 6 bright colors, in addition to the 8 saturated colors that are shown in the upper figure. The extra colors are bright red, bright yellow, bright green, and strong blue. In addition, they are supplemented by the human skin color and the foliage green color. Another method is known as color quality scale, or for short CQS. It is NIST in close cooperation with the lighting industry and the CIE, whom are in the process of finding a solution to the unsatisfactory measurements using CRI. The problems of CRI occurs especially when the method is used for the characterization of solid body light surges. To meet this new technology, which includes LEDs, CQS is a possible solution. The method which CQS is calculated derives from modifications to the method already used in CRI. CQS can most likely be a new international standard either in addition or as an alternative to the older characterization methods. Here we compare CRI and CQS with each other. It is evident that CQS provides significantly lower values than the CRI method does. Therefore, LEDs and other solid-state light surges are not currently measured properly. But if the CQS method was introduced, the measurements might be more accurate. This illustration shows how the colors are reproduced at the different values. Shown are 8 random colors that are independent of 8 standard colors of the RR index. This was a review of the basic parameters of light. To see more videos and keep up to date now and in the future, please subscribe to this channel. Also, if you have any comments, please write it below.